Hi, and welcome to this next video where we're going to look at the AdaBoost algorithm. So let me first try to just motivate it a little bit. So previously, right, we looked at linear models quite a number of times. We also looked at decision trees, but in particular, there were some issues with linear models is that, maybe sometimes the data is not really linearly separable or close to linearly separable. So for instance, this data set that you see here, if you try to run logistic regression, you'll get the line that's plotted here, which is not really doing that great. Of course, you can see here, if I really wanted to use a linear model, I could use a feature transform first. It does seem like, the lower left rectangle is all the blue points and the remaining parts are all the red points. So perhaps if I first did the feature transform, mapping a point x, y to the maximum of x, y, then these points that are sitting down here in the lower rectangle will be mapped up before all the red points. So, of course, I could have done this. But I guess some issues that we talked about before is that, well, as soon as I start doing feature transforms, in particular, if I introduce a lot of new features to make sure that I have the features that are useful for the data, I might risk overfitting. And of course, also the second issue is that you need to handcraft features. And in this particular case, I looked at the data and used knowledge of the data set in order to design these features. So of course, there's some issues. Some of them can be dealt with, but we'll see another approach here, another way to deal with this issue. Right. Also, one more issue with linear models is, in particular, if you are doing gradient descent for logistic regression, for instance, the gradient descent implementation is going to be sensitive to the scaling of the features. So if you don't first scale your data set, then, maybe the performance will not be so great. So, but the next observation here that we're doing here is that, okay, if I just train a linear model without doing any feature transforms whatsoever, then, well, it's doing a little bit better than guessing, right? It's not completely horrible, but it's just not great. Okay, so it's a little bit better than random guessing in the classes, right? So just say it predicts blue below the line and red above it, it's going to get more than 50% of the training data correctly, right? And this is close to what has been defined as a weak learner. So boosting, which is the topic of this video, AdaBoost in particular, is basically a technique for taking something that's a weak learner, meaning something that's a little bit better than guessing, and turning it into a strong learner, which is something that performs really, really well, just said loosely. And so for this video, we're going to focus just on binary classification, just to keep things simple. So for this video, a weak learner is a classifier that does slightly better than guessing on a training data set. Okay, and a strong learner is something that perfectly classifies the whole training data. And maybe let me just add a word of warning here that if you go in the literature and look up the definition of a weak learner and a strong learner in the classic setup, this is not the exact definition. This is a kind of like a simplified definition. It is really what you're using in the proofs of these weak to strong learner transformations that are known in old classic theory of boosting. But the basic idea is this one, right? That weak learner is something that does better than random guessing on a training data set. And a strong learner is for our purposes, something that perfectly classifies the training data. Okay, so this will be sufficient for us, and you can go and look up the original definition if you're interested. But this is the property you're using, basically. Okay. So what do we have, right? So boosting is a technique for taking such a weak learner, something that can do slightly better than random guessing, has a slight advantage, and then combining these into something that are using it to come up with something that actually can perfectly classify the training data and hopefully also performs well on new data. So the question, of course, how is this done? Right? And the basic idea is that in boosting is that we're going to combine a collection of weak learners. So we're going to train multiple weak learners, multiple hypotheses that do a little bit better than guessing, and then we're going to combine them into what we call a committee or an ensemble or a voting classifier. So we'll see what this means. And the basic idea is that they will vote. You'll train a bunch of these weak learners, a bunch of hypotheses, and then they are going to vote, like we saw in the bagging and random forest video just before this one. Okay, so let's do a little bit more details, dive into the details of this. So boosting is, in some sense, a meta algorithm. So it's basically, it takes as input one learning algorithm, and then it builds a new one from it. So you have a base learning algorithm A. This is the weak learner, the one that can do a little bit better than guessing. And this base learning algorithm outputs hypotheses from a set H, right? So maybe Your base learning algorithm is decision trees. Maybe your base learning algorithm is linear models where you take the sign. So you have a base hypothesis set from which the base learning algorithm outputs its hypotheses. And now boosting, the basic idea in boosting is that you are going to run this base learning algorithm t times for some t that you choose. Or maybe you can stop based on validation and so on. But you're going to run the algorithm t times on different data sets. And of course, I haven't yet said what those data sets are, but you're going to run it on different data sets. And then each of these iterations of the base learning algorithm are going to output a hypothesis each, right? H1 up to HT. Now you're somehow going to compute some weights, alpha 1 up to alpha t, one for each of these hypotheses that you trained. And then the final classifier that you're going to use to make new predictions is the one where you return the sign, where you sum over all these t hypotheses, you weigh them by the weight alpha t, and you take the prediction made by that hypothesis. So what you can see here is that this is basically a weighted majority vote amongst the classifiers. So if all the alphas were the same, then we basically just by taking the sign, we're just checking are there more minus ones than plus ones. If so, we're going to return minus one, otherwise we're going to return plus one. With these weights, it's just a weighted majority vote. So some of these hypotheses can be made more important than the others, so their vote counts more. Okay, but that's all that's happening here. And if we compare this to bagging a random forest, what we did there was that we ran a base learning algorithm A, t times again, on subsample data sets, right? So we randomly sampled a subset of the input data set, and then we ran the base learning algorithm on these subsample data sets, returning hypotheses, one for each of these subsample data sets. And the final classifier that we use, if it's a classification problem, is just a simple majority. So there are no weights here. It's just the sign of the sum of these predictions made by these t hypotheses. Okay, so you can see that it has very much the same structure. The difference between boosting and bagging and random forest is in both what is its data set that we're training on. Down here we subsample, up here we do something else. And also that we have these weights up in boosting, but it's kind of the same style of algorithm. Okay, so weighted data sets. So what we're going to do is we're going to, in this AdaBoost algorithm, or boosting algorithms, we're going to see that if we have a training data set of n examples, xi's being the feature vectors and the yi's being the labels, like we're used to, then we're going to work with the probability distribution over the training data set x. So we think of it as if there's a distribution D, and it's just a probability distribution, so it's non-negative numbers, one for each of the training examples, and the weights sum to 1. So we can kind of imagine it like this, that each of these points in the training data set are weighed differently. So some of them have a huge weight, and some of them are really small. And we should think of it as if we make a mistake on the ones with a large probability, then this is much worse than if we make a mistake on the ones with a small weight. And now for such weighted data sets, what we're going to look at is we're going to look at minimizing the weighted 0-1 loss. And the weighted 0-1 loss with respect to the distribution D, we'll just denote it by this, L sub D of H, is just the normal 0-1 loss. But with every mistake that you make, this is the indicator, right? That's 1 if you misclassify the ith training example using the hypothesis H, you weigh it by this probability. Okay, so if it has a large probability, it's going to be more important in the 0-1 loss. It's going to cost us more. And here the obvious observation is that if D is the uniform distribution, meaning you put 1 over n on each training example, then of course you recover the original standard 0-1 loss. Okay, so it's just a way to put more emphasis on some points than others. Okay. And just a short remark that all the learning algorithms that we've seen so far, they're basically easy to adapt to this weighted setup, like decision trees. Whenever you make a split and you test how good the quality of a split is, you just have weights on the points in the subtrees, and everything just carries through. It's not a problem to adapt the algorithms we've seen so far to this setup. Okay, so boosting again. So we want to run this algorithm A, the base learning algorithm, t times, and what we're going to run it on is going to be reweighted data sets, right? So this is basically what we're going to do. We're going to put different weights on the points in the training data set, and then we're going to train all these different weighings. And this is going to output hypotheses, h1 to ht. We're going to compute some weights, and we're going to return a majority vote. So So let me just say, if you look at bagging random forest, one can actually think of bagging and random forest as a special case of reweighing as well. So recall, right, that what we're doing in bagging is that we're going to sample n prime training examples from the training data set, but we're going to sample with replacement, right? So you can sample the same one multiple times. Now, one can actually come up with a way to just think of this as just training on a reweighted data set. And the intuition is just, if I have an original training example, xi, yi, and I sample it ti times, I could have also defined a probability distribution where I put a weight of ti over n prime mass on that one point. And, you know, so if it's not sampled at all, it'll get a weight of 0. And if it's sampled multiple times, we'll get a higher weight. And the claim here is that, okay, if I look at the 0-1 loss on the subsample, so these primes here, the one that you normally run bagging on with standard 0-1 loss, then that 0-1 loss is the same as the weighted 0-1 loss for this weighing down here. So you can think of what bagging is doing is really also just training on a reweighted data set. Maybe just to see that this is actually the case, here is the 0-1 loss that you would be minimizing for the subsample data set, right? You have 1 over n prime points, and you do the average with the 0-1 loss on all these examples. Now, okay, so we can look at the contribution for any original input point, xi, yi. You can see how many times does it appear up here in the first sum. Well, it appears ti times. So this is exactly the same as the line above here, right? Because the term for xi, yi, the original xi, yi appears ti primes by definition of ti. This here, we can move the 1 over n prime inside. And now you can see that this factor here is just the probability distribution we defined in this di down here. So this is really the weighted 0-1 loss with this weighing that we defined down here. So really one can think of bagging as you're repeatedly sampling, so to say, a new distribution, a new weighing on the input data. And then you're training on these different weighted 0-1 losses. Okay. Now, in boosting again, right, so we want to train on these reweighted data sets and compute some weights. So there are a couple of things to fill out here. Of course, right, how do we choose the weighing on the training data in each iteration? That's the first thing that we need to fill out before we have a complete algorithm. And also how to choose these weights alpha-1 to alpha-t that we put on the hypotheses, right? These are the two things that we need to define. So, and let me just give it to you. Here is AdaBoost, the classic algorithm for boosting. And so what it does is the following. So let's try to pass it. It's a little bit lengthy, but we'll get through it and work through an example with it. So if you have your training data x1 up to xn with labels y1 up to yn and a base learning algorithm A, then in AdaBoost, you start by initializing this probability distribution to be the uniform distribution, just 1 over n probability on all the points, which makes perfect sense. And now you're going to loop for t iterations, also as the template before suggested. We're going to run the learning algorithm A to minimize the weighted 0-1 loss using the probability distribution for the tth iteration, right? So in the first iteration, we're going to use the uniform distribution. This, of course, outputs some hypothesis that we call HT. Now, what we do then is that we compute what is the error of this hypothesis that we just trained. And the error that we're computing is with the weighting that it was trained on. Right, so we just compute what is the weighted 0-1 loss for the hypothesis we just found. Right, so it's just this sum over all the training examples, the weight that we put on it, and the indicator for whether we mispredicted this, this example using the t hypothesis, the one we just trained. Okay, so we start with the uniform weight, we compute the weighted loss of the one we just trained. And then the next step here is that we somehow set these alphas as, okay, it's an expression that depends on this error, right? So a half log 1 minus the error over the error. And at this time, this could seem like a magic constant, but in the next video, we'll try to go through a more detailed analysis and show that this constant actually makes sense. Okay, but for now, it's just somehow a constant that we compute that depends on the quality of this hypothesis HT, how well it performs with respect to this weighted 0-1 loss. Okay, now that we have this constant, what we're going to do is that we're going to reweigh the data for the next iteration. So here we set the values in the next iteration for the next reweighing of the data set. And what we do is we set the weight of the ith training example to be the weight that it just had, right? So this is the weight in the tth iteration. And then what we're going to multiply it with this expression here. So e to the minus this constant alpha t, yi is the label of the point, and the prediction ht of xi. So we're going to multiply it with this, and we're dividing by this set t. And what this set t is, it's just a term that makes sure that it stays a probability distribution. Right? There's nothing special here. It's just sums over all the examples of basically what we have up here in the numerator. And you sum all those values, and this is what you divide by, making sure that you again have a probability distribution. And also maybe one thing to remember is that the exponential function is non-negative, so it remains non-negative numbers whenever you do this rescaling. Okay. So of course, right, it's still not clear that this is a good choice of reweighing, but I think for now, and we'll come back to that in the next video, but for now, we'll just try to see what this algorithm actually does, right? And at the end of this, you return the hypothesis that we claimed, this weighted majority vote. Okay, so that's the AdaBoost algorithm. Okay, so let's have a small look. So the new weights here, they're updated like this. I guess this is the most interesting part of the algorithm, that you reweigh the data. And so let's try to see what happens here. So what you see here is, at least assuming that this alpha t is a positive number, and it will be if you're better than guessing, we'll see that, but let's return to that later. So what we see here is that, well, if we examine this exponential expression in here, right, that I guess the two cases, so the label is a -1 + 1 label, and the prediction is also a -1 + 1 prediction. Okay, which means that, well, if they happen to be equal, which means that you make a correct prediction on this data point, then what the factor that you multiply with here is e to the minus alpha t, right? And also the division by set t. The intuition being here that alpha t is going to be a positive number, and what you're going to get here is that you're going to reduce the weight of this training example. And on the other hand, if the prediction is wrong, so the yi is not equal to the ht of xi, then the product yi ht of xi, one is -1, one is +1, so this is going to be -1, which means that the weight that you're going to put is e to the alpha t. So in some sense, right here, you're reducing the weights, but you're dividing by e to the alpha t, and here you're increasing by e to the alpha t. Which means that the intuition is that the algorithm, what it's going to do is it's going to put more weight on the points that you misclassify. It seems like a very natural strategy. You put higher weight on things you misclassify, lower weight on things that you got right. And what this means is that in the next iteration, the base learning algorithm will focus on the points that have been misclassified before, right? And the more iterations that a point is misclassified in, the more weight it's going to have, right? So it's going to be more and more important in these weighted 0-1 losses. That's the basic idea. Okay, so I think now we'll run through an example and perform in the next video where we will cover the analysis and show that this is a sensible choice of scaling parameters. So let's see an example execution. So what we're going to do here is let's say that the base learning algorithm is decision stumps. Okay, so we have two-dimensional data, there are two features. And what we're going to have is as our learning algorithm, we're going to have, or our hypothesis, we're going to have decision stumps, which means that we have one root where you ask whether a given feature, either the x feature, the y coordinate feature here, is less than or equal to a fixed value, right? So we had a video, one of the first videos was on decision trees and on how to train these decision stumps. The basic idea and how we chose or trained such a model was that we figured out what is the best question we can ask in the root, right? So a question corresponds to any of one of these different lines here, or a vertical line. So what we did was we said, okay, for every feature of the data, in this case, there are two features, the one on the x-axis here and the y-axis here, we looked at all the splits between all the n-1 relevant splits between the training examples. And for every one of them, we try to create a decision stump where this is the question we ask in the root, right? So we partition the data into two halves along this line. And then we look at, okay, if I make this partitioning, I know which points end up in the left leaf. I know which point end up in the right leaf. For each leaf, I can look at what is the best prediction to make in this leaf with respect to this weighted 0-1 losses. Nothing hard in looking at this. You just look at, is there most weight on elements with label +1 or elements with label -1 in this leaf. We choose the best answer, and we can compute the final accuracy of this, or the final weighted 0-1 loss of this decision stump. So this is just straightforward, just to adapt the algorithm for decision stumps to work for the weighted 0-1 loss. So this is the one we're going to use. We're going to just try and run AdaBoost with decision stumps and see what happens. Right, so decision stumps, if we visualize it, it will look something like this, that the hypotheses will correspond to all axis parallel hyperplanes aligned. So you can draw a vertical line or horizontal line and classify, and then choose the classification on the two sides of the line. You could actually also return blue on both sides if you wanted to. But these are basically what it's going to look like, right? You have these vertical splits and horizontal splits, and you can choose what to return on both halves. So this is what decision stumps correspond to. So we're going to try and run AdaBoost on this training data set here. So we have some data here. It's clear that there's no decision stump that gets this perfect. So let's try and look at what is the algorithm doing, right? The algorithm tells us, if we look at it again, we start by initializing a weight of 1/n on all the examples. And then we have to train a classifier to minimize this 0-1 loss with this weighting. So this is what we do. We start by putting a uniform weight on all the points. They all weigh 1/10. And then we find the best decision stump for this weighing of the data. And you can see this one here, the one that we drew here, only makes 2 mistakes. So it's weighted 0-1 loss is 2 out of 10. And I think you could also see that there are no better decision stumps you can make. Any decision stump that you train here would misclassify at least 2 out of the 10 points. So this is one we could get from the first round of training. And then we have to compute. AdaBoost tells us to compute what is the error of this hypothesis on this with respect to this weighted 0-1 loss. In this case, it's easy, it's 2 out of 10. And then we had this magic constants, which was in the algorithm, it's a half log of 1 minus the error over the error. Okay, so what is this, right? So 1 minus the error, that must become 8/10, right? So 8/10, and the error is 2/10. So if we divide the two, we get 8/10 in here. This is roughly 0.69. Okay, so this is the first weighing alpha 1. And now the next step was to reweigh the data set. So remember again, right, that the points that we classify correctly are the ones that we misclassify. We have to scale up their weight by e to the alpha 1. If you look at this, this is log of 4 with a half outside. We can move the half inside to become a square root. So then we get log of 2. So e to the log 2 is just 2. So, and e to the minus alpha 1 is a half, which means that every point that is misclassified, you need to scale up its weight by a factor 2. And every point that is correctly classified, we scale down the weight by a factor 1/2. So you can see here, right, we have these 2 blue points up here that are misclassified, and their weights will have to scale by a factor 2. So this is a typo. This red point should, of course, have been a 0.5. It's just a typo. So a factor 2 up, a factor 2 up, the rest go down by a factor 0.5. These are the only 2 misclassified points. So if we do this, we'll see that, okay, we have to compute this normalization factor ZT to make sure that everything is a probability distribution. So we have to look at all these enumerators here. So there are only 2 points whose weight go up by factor 2. So the formula down here is correct. It's just a typo on this one label over here. So there are 2 points whose weight was 0.1 before, and we multiply them with 2. And there are 8 remaining points had a weight of 0.1 are now multiplied with 0.5. So this normalization factor is 0.8. So we have to divide by 0.8 in all these expressions here. And if we do this, we basically get these values here. So these 2 points here, the ones that were misclassified, now have a weight of 0.25, and the remaining have a weight of something 0.06, something with a few more decimals that I just ignored here. Right, so this really means that after this first round, we put a much more emphasis on these 2 misclassified points. We down-weighted the others. Okay, so that was the first 1 round of AdaBoost. So let's do 1 more round. So now we have to train a decision stump on this weighted data set here. And the best thing you can do here, you can see, is the best you can do is that you can misclassify 3 of these small points down here. right? These three small ones here. This is all, right? You have to get the two big ones correct, because otherwise they weigh more than even those three small ones. So the best you can do is something like this. Good. You'll always get three small ones wrong. So, okay, so this is a decision stump we can train with this weighing. So let's see what happens then. Then we compute the error again, right? So we have to, the weighted 0.1 loss, so here's 0.06. There's some decimal points that I ignored. So if you sum them up with the real weights, you would get roughly 0.19. Okay, so this error is 0.19. It's the sum of the weights on these three red points here, 0.19. Then you compute this constant, a half log of 1 minus 0.19 divided by 0.19. If you type that into a calculator, you'll get something that's about 0.73. Okay, which means that the points that you misclassify, you have to multiply their weight by each of the alpha 2, which is basically 2.08. And the ones that you get correct, you have to multiply their weight by roughly 0.48. Okay. So as you can see here, right, the only ones that we get wrong are these three ones here in the middle. Okay, so their weights are gonna change from, you have 3 points down here. You can see in this, we're computing what is the normalization term, the 3 points that were 0.06, and you have to multiply the weight up by 2.08. Okay, you had the two big points, the one with weights 0.25, the two of them, and you have to downweigh them by a factor 0.48. And finally, there are the remaining 5 points, and those 5 points had a weight of 0.06, and they are downscaled by 0.48, giving a final normalization term of 0.76. Okay, so basically we have to multiply the ones that we get correct by 0.48 divided by 0.76, and we're going to multiply the ones that we get wrong by 2.08 divided by 0.76. So this is what happens here, right? So these are the ones, we have these 5 points that are correctly classified. They were also correct before, so now their new weights are 0.06 times 0.48. This is the factor for being correct, and the normalization term 0.76. Okay, we had the two ones that we had wrong before that we weighted higher, and they're now correct. So now we multiply 0.25 times 0.48 divided by 0.76, being roughly 0.16. Finally, we have those 3 points. There were 0.06 before. They're wrong this time, so we multiply with 2.08, and we divide by the normalization factor, giving us also roughly 0.16. So this gives a new weighing where we have these 5 points here that have really small weights, only 0.04, and then we have another 5 points in the middle here, have a pretty large weight, of 0.16 weight. Okay, one last round. So we run boosting again, or we train a decision stump. And of course, right, these big ones, they matter a lot. So this decision stump here is really good in this data. It misclassifies a point here with weight 0.04, and it misclassifies these 2 points down here with weight 0.04 as well. Everything else is correct, which means that the error here is basically the 3 points with a weight of 0.04, so it becomes 0.12. And this means that you compute the alpha 3 half log 1 minus 0.12 divided by 0.12, which is roughly 1. And I think let's stop here. So we don't want to do, let's just not do the last reweighing. Now we know what the coefficient is, at least on this hypothesis, the third hypothesis. Let's stop here and see what happened, right? So we ran AdaBoost, and what we saw was the first round we trained this decision stump, and we've computed a weight of it of 0.69. Next iteration, we computed this decision stump. The weight was alpha 2 being 0.73. And lastly, we computed this decision stump with a weight of 1. So the final classifier now, the one that AdaBoost returns, is the one that takes the sign of 0.69 times the prediction of the first hypothesis plus 0.73 times the prediction of the second hypothesis plus 1 times the prediction of the last hypothesis. Maybe we can try to just look at the different regions of, if we ask it to classify a point in any of these different boxes here, what would the classification be? Right. So if we look first in the top left corner here, you can see that the first hypothesis predicts class 1, and class 1. So you basically get each of these terms, the predictions by the hypotheses, the base hypotheses are all 1. And so we're going to return the sign of the sum. And this is, of course, positive, so we get a 1. Over here in the next one here, we'll see that the first hypothesis predicts -1. So we get a -0.69. The second one predicts positive, so that gives us a +7.03. And the last one also predicts positive, that gives us +1. So this is still positive, and we're going to predict 1 in this region. In the final top right corner, we're going to see that both of the first and the second hypothesis make a negative prediction here. So we get -0.69 minus the weight 0.73 plus the weight 1 from the last hypothesis. This is still negative, so we make prediction of -1 in this region. Down here, we'll see that the first two have a positive prediction and the last one has a negative prediction. The sign of this 0.69 plus 0.73 minus 1 is still 1. So we'll go with that. We take the middle box here. The first one has a negative prediction. The second one has a positive prediction. The last one has a negative prediction. The weighted sum is negative, so we get a -1. And finally, the lower right corner, all of them make a negative prediction, so we get a -1. And as you can see here, this combined classifier nicely, perfectly classifies all this data, right? It actually creates this decision boundary that does not correspond to a decision stump, and that perfectly classifies this data that we just saw. Okay, so this is AdaBoost. You just run these iterations where you reweigh the data set each time, where the weights depend on whether you classify correctly or incorrectly. You upscale the weight of misclassified point and you downscale the weights of correctly classified points. In the next video, we'll try to give some theoretical proofs that this actually, after enough rounds, it will produce a classifier that perfectly classifies all of the training data, as long as each of these runs of the base learning algorithm gives something that's better than guessing.